My name is Parker Fritsch, and welcome to my presentation on the synthesis of Benzil from the reactant benzoin. I hope you enjoy. Alright, so pictured above is the desired product of this reaction known as Benzil. As I mentioned before, we're going to be turning benzoin into Benzil pictured above. So I figured in order to get a good comprehensive understanding of what we're doing and why we're doing it, it is important to understand what the actual compound Benzil consists of. So Benzil is an organic compound with the molecular formula C14H10O2. It is soluble in benzene and diethyl ether. It has a melting point of 94.8 degrees Celsius, a density of 1.23 grams per centimeter cubed, and it has an overall molecular weight of 210.23 grams per mole. Additionally, you can notice on this compound that it has two identifiable ketone groups that makes Benzil known as a diketone compound. That is going to be important for the overall reaction because, as you'll see in the next portion of this video, we're going to be turning benzoin, which has a alcohol group on it, into Benzil. So we're going to have to oxidize something, and that something is going to be that alcohol group. So let's go ahead and take a look at benzoin. Alright, so previously mentioned, this experiment is going to be about the synthesis of the product Benzil from the reactant or starting material known as benzoin. So just like Benzil, benzoin is an organic compound. It has the molecular formula C14H12O2. Notice how similar those molecular formulas are. That's because benzoin has two additional hydrogens, one of them being on that very identifiable alcohol group that you can see in between the two phenyl rings and next to one of the other ketone groups. Here in this experiment, in order to achieve the product Benzil, which has two ketones, known as that diketone as previously mentioned, we're going to be oxidizing that alcohol group on benzoin and turning it into that second ketone group. So previously mentioned, that's how we're going to be able to get Benzil, that diketone compound. Benzoin, our reactant, has the molecular formula, again, C14H12O2 with two additional hydrogens added to it, not carbon, excuse me. It has a density of 1.31 grams per centimeters cubed. It has an extremely high melting point at 137 degrees Celsius, a molar mass of 212.24 grams per mole, and a boiling point of 344 degrees Celsius. And for those of you that prefer the IUPAC name instead of just the general chemical compound name benzoin, you can use the IUPAC name 2-hydroxy-1,2-diphenylethanol. So now let's go ahead and let's dive into how we actually synthesize Benzil from benzoin. Alright, so unfortunately I don't have the ability to draw on this animated video, but I want you to take a look at the above NMR spectrum for the desired compound Benzil, the desired product. I wanted to showcase this to you because it is important to note that after we synthesize Benzil from benzoin, the reactant, we want to be able to confirm that we actually did get Benzil out of our reaction. So one of the ways you can do that is by using the NMR, which is pictured above, and you can confirm it by noting the triplet, which is going to be the two hydrogens that you can see on the outside of the benzyl ring. The hydrogens in this case are going to be equal on both phenyl rings just due to the fact because on both sides it is a ketone group, so there is no variation in them. So the triplet is of the two carbons on the far hand side away from the ketones, the doublets, which are going to be on the far left end of the NMR spectrum, and that's going to be actually the hydrogens that are going to be the closest to the ketones. And then the last triplet that you can see on the far right of the NMR spectrum, that triplet is going to be the hydrogen that is at the very tip at the end of both of the phenyl rings. Okay, so at this stage in the video, we have already discussed the actual composition of the desired product, that diketone compound known as Benzil, as well as the composition of our starting material known as benzoin. We've also discussed that confirmation NMR step, which can be used to actually confirm that we have our diketone product known as benzoin and not benzyl or a compound with other impurities. If we had Benzil, for example, you would see a couple more peaks indicating that we have a few additional hydrogens in the overall molecule, which is not good in terms of the fact that we were trying to achieve a different product known as Benzil. That Benzil, having the absence of that alcohol group that benzoin has, is going to have fewer hydrogens than benzoin. So now that we've already made that discussion, we're going to go ahead and jump into the actual reaction pictured above, which is the overall synthesis of Benzil from our starting material, benzoin. So we're going to start off with the step known as the condensing of benzoin. Here in this step, we took thiamine hydrochloride, turned it into thiamine, which is what we're going to use. We're going to use 3 molar sodium hydroxide, 2.12 grams of benzaldehyde, and 95% ethanol. I'm not going to go through the entire procedure just because we don't exactly have that much time for it. However, I am going to say the condensing of benzoin needs to be done with the precise measuring of the pH range, because we need it to be in between the pHs of 8 and 9. If it is under the pH of 8, the reaction will proceed at an extremely slow rate, which is undesirable. And if we have a pH over 9, it is going to be undesirable again, because we have what's called a Cannizzari reaction, which is going to compete with the overall synthesis of Benzil, which is our desired product. So that actual step is not mentioned in the above photo, because that's how we condense benzoin for this reaction. What is pictured above is the overall synthesis of the nitric acid, which is that molecule that you can see with the nitrogen, and it's going to in this it shows it binding to that oxygen, which is okay, but that's not exactly what it's supposedly doing. It's actually going to attack those electrons on the hydrogen. It's going to do a series of nucleophilic attacks and substitutions and attacks again and deprotonating, and then we're going to get to that overall structure down at the bottom where we can see that nitric acid is all by itself with that arrow pointing from the oxygen to the nitrogen. And the overall product, the diketone compound known as Benzil, meaning that that nitric acid has effectively oxidized that alcohol group on benzoin to form the ketone functional group on Benzil, which is the overall goal of this reaction, and is what I mentioned in the previous steps of how we're actually going to get Benzil from benzoin. And we can go ahead and we can run this compound that you see above through a mass spectrum, through an IR, and through a hydrogen NMR, and we can compare it to the actual mass spectrum, the IR spectrum, and the HNMR, which I have previously shown you for the actual compound of Benzil. And we can see if our results indicate that we do have a compound that is suitable enough to be Benzil, if all the data ranges match. So now I'm going to jump into the next portion of the video, which is going to showcase how we are going to do the same reaction, but in a more environmentally friendly method to reduce the amount of waste, to drive the reaction at a faster rate, which is actually only going to take 2 hours instead of this method, which it took us around 3 to 4 hours. And it also produced more of the desired compound Benzil. So let's go ahead and let's take a look. Alright, so in the previous portion of the video, I did mention that a catalyst would be added, the MgO. That was incorrect for that portion of the reaction. That reaction is going to have the nitric acid. That nitric acid is a extremely volatile compound, very irritable, very harmful for our environment. And the overall goal of green chemistry is to be able to synthesize the same product, if not even better products, with the overall goal of producing less waste, or if we have to produce waste at all, a less harmful form of that waste. And that's what we're going to be discussing here in this reaction pictured above. Notice instead of using the nitric acid, we're going to be using the nanocrystals of MgO. Those magnesiums on the MgO catalyst are going to allow for a more controlled environment in the synthesis of Benzil. Those magnesiums are going to have a greater selectivity compared to the nitric acid before in the other reaction, and that selectivity allows for a less overall reaction time. This reaction should only take about 2 hours compared to the one with nitric acid, which should take a student or scientist in the lab anywhere from 3 to 4 hours to complete, and that's not even necessarily with a good percent yield either. This one with the nanocrystalline MgO should give you a high percent yield because in the research paper that will be shown on the next slide in the references, the percent yield was around roughly 98%, and it actually yielded more than the nitric acid method. So that is, much more superior to the nitric acid just in getting the product, but it also was able to form less waste than the nitric acid method, which makes what the goal of green chemistry is all about for this reaction. We were able to take the same reactant, use different methods for the mechanism and the synthesis of Benzil, and still come out with a competitive / the same product known as Benzil. And that within itself is what this module in our organic chemistry class was all about. And it's been the message of our class for the duration of the semester, is to be able to take a reaction, see how harmful it can be to our environment, and if there's an alternative. Here in this case, we have the alternative to use those nano MgO crystals, which are more selective, they produce less waste, and they allow the reaction to occur in less time, making it a more suitable reaction for scientists and students to do in the lab. However, it's a little bit more challenging for students to do in the lab because it takes a little more finesse to use the nanocrystals compared to the nitric acid. But overall, this reaction is much more safe for the environment and is much better at getting a higher yield of a crude product. So thank you for your time. I hope you enjoyed this presentation. In the next portion of the video, I'm going to show a video about a teacher who is going to film all the steps of how he turned benzoin into Benzil with the steps mentioned in this video. Now that we've concluded this presentation on the synthesis of Benzil from benzoin with both the original nitric acid method and the greener chemistry version with magnesium oxide, I want to showcase this video from Matthew Kenslow and how he synthesized the same reaction, turning benzoin into Benzil. So take a look and enjoy, and thank you for watching.